He's here in spirit, and we're really excited to have him present his work on collective behavior and how people coordinate together. Robert is, as of 2 days ago, professor at University of Wisconsin-Madison. Previously, he was a postdoc at Princeton, did his PhD at Stanford. And I also found out this morning at breakfast that he was a research assistant with Ann Candler at Santa Fe Institute as an undergrad when he was at University of Indiana. So Ann sends her regards. And we're really excited to have you present your work today. So let's give the stage to Robert.
Hey. Nice to see you all in this little tiny video. Yeah, I am very sad that I can't be there. I'm feeling a lot of FOMO. Reading the updates on Slack and whatnot. But I'm going to do my best to kind of still link minds, I guess, in some way. So my work focuses on the kind of link between individual cognition and group kind of behavior. And within this frame, this phenomenon of collaboration, right? The ability of groups to work together toward a common goal is a real engine of human culture. So we use language to teach, to plan, to persuade, to delegate and clarify and confide in one another. And when this works, it's pretty awesome. We can like build skyscrapers and cure diseases and, help each other through these, these difficult times that we live in. But at the same time, communication and collaboration isn't always easy. So especially when we find ourselves faced with, complex concepts like trying to talk about what we like about a particular beverage that we've had, maybe cutting edge research, like I can't read a word of this abstract, apologies to biologists. And, when we have these kind of intractable political debates that feel like we're kind of stuck on different wavelengths and communication breaks down and we can't seem to share a goal or work together. So I'm interested in the things that make collaboration challenging and how we can overcome them. So, broadly, the goal of my work is to understand the computational principles lying behind the challenges of collaboration and the cognitive mechanisms individuals have that allows us to do a pretty good job under really difficult circumstances. So one of the basic kind of principles that I'm building on is this idea of social inference, or sometimes known as theory of mind. So this is the ability to not just treat one another in terms of our like surface statistics of our external behavior, but to maintain representations of what might be going on inside other people's heads. And this is a little diagram from a paper by someone that might be in the room right now, Julian, that I think kind of illustrates the components of this really well, which is, there's all of this stuff inside an agent's mind, their beliefs, their desires, the things they can see and can't see, and all of these lead them to take certain actions, which then feed back on the world that they're and the environment that they're in, which updates their beliefs and so forth. So there's this really nice way computationally of writing this down as an inverse inference problem. So essentially, we see actions, but we want to make guesses about what's going on inside the box. And people are pretty good at this. So I'll illustrate some kind of more concrete cases of this in the future, but the main thrust of this argument is that once we start understanding individuals as fairly sophisticated social reasoners, as opposed to kind of heuristic agents simply kind of reacting to the surface statistics of one another, I will argue that we can understand a lot more about how groups work when you kind of percolate individuals with these more sophisticated capacities through the system. So I'm going to highlight two projects that I think kind of help illustrate this in different ways. So the first case is illustrating how social inferences have important consequences for collective behavior in environments where you can't actually see the rewards that other people are getting. So we often think about these kind of game theoretic cases where there's kind of public information about the rewards of other people, but a lot of that machinery breaks down when there's private information. And then in the second case, I want to extend this to the ability to communicate when we don't have great words for things. So this is unfortunately often the case that we're in. We're having to talk about new concepts, and I'll argue that the ability to make inferences about the kinds of concepts and meanings that other people will understand allows us to kind of overcome these challenges of communication. Okay, so how do we study this case where rewards are hidden, and how do we know if social inference is helping? Well, we set up a task. It's called a collective sensing task. It may be familiar to those of you who are embedded in the animal behavior literature. So we kind of took inspiration from Andrew Birdall and Ian Cousins' work on fish schooling in, I think they're zebra fish, finding patterns of light in a tank. So essentially, participants were connected over the internet. They were put in their own little tank, controlling a little avatar. So they could click to move around this environment. And their goal was to get points. And points were scored only in a certain region that was moving around over time. So they couldn't see where the points were, so they had to go find it, okay? And they could see when they entered this little scoring region, but they don't know whether other, they don't see it when other people are in that region. So here's a little video. You're gonna see a triangle moving around, looking for this, this dark gray spotlight. And remember, I'm showing you the dark gray spotlight, but they don't see it as gray. They only know if they enter it. So you see, oh, they found it. They're looking, they're looking, they're looking. Oh, they found it. Right. So they're doing a pretty good job, but it's hard. It's a big tank and the spotlight's kind of little. So they're doing about as well as any individual person can do. But what I want to show you is what happens when you have more agents in this tank playing this game together. So this is exactly the same task with the same spotlights, but now there's 5 agents. Okay. And what we're interested in here is the average performance of the individuals. So basically, what score is the average person in this group getting compared to the average person in a smaller group, like one with 2 people or just 1 person? And intuitively, you can see there that there's some pretty interesting dynamics going on there. Yeah, so do they do better, I guess is the question. And you may have some guesses about that. But first, I'm going to show you some predictions under different computational models. So we took a kind of basic set of heuristics that are common in the social learning strategies literature. So a naive copy heuristic is one where a agent just randomly picks another agent to copy or explores. Move to center heuristic is the main thing that's used to explain fish behavior. So this is essentially tracking the centroid of the group and being biased toward that centroid. And an asocial model, of course, is one that doesn't attend to other agents at all. So it's just exploring like a solo person did. So good sanity check there. You notice that on the x-axis is the size of the group. So the asocial model doesn't have any improvement or decrease in average score as a function of the group size because they're ignoring each other. You see that the naive copy heuristic and the move to center heuristic get a little better as a function of group size, which is kind of reproducing the benefits that you see in the social learning strategies literature. But this social inference model, where agents are using the observable trajectories of other agents, essentially like when they slow down, when they speed up, when they stop, and change course, to infer what the reward that other agents are currently getting. So essentially, like the intuition here is that if you see an agent kind of suddenly stop and start to like move in a local region, you might guess that they're more likely to do that if they're currently getting a reward than if they were kind of just like going straight across the map. Okay, so what did the empirical data look like? Well, this is a challenging study to run because you have to connect all these people for these 5-minute sessions, and bigger groups are harder to recruit, of course. But what we found was pretty strong evidence favoring the social inference model. So the way we know this is that there are certain thresholds of scoring that humans achieve that basically under no parameter values these heuristic models can achieve. So you can search over all different exploration rates, all different kind of amounts of bias to the center, and this is the best they can do. And only the social inference model is able to kind of exceed that ceiling. Okay, so there's some evidence here that the ability to make these social inferences about the private information that another agent might be experiencing allows groups to scale better as a function of group size. So the kind of rewards that accrue to bigger groups are kind of accelerating at a faster rate. But you might worry, okay, this is a really simple task, right? There's just this deterministic blob that is determining reward. What if it's noisier, right? Real world environments have a lot of kind of false alarms. So we started looking at these more continuous gradient landscapes. So in the low noise condition, you can see we essentially put a Gaussian around that spotlight and added noise to it. And then in the high noise condition, we did the same thing, but the noise was a lot higher. Okay, so this is like, there's going to be all these little local maxima scattered around the environments, even if there's kind of like a hot spot where that spotlight would be. Okay, so how do human groups do in these kinds of environments? We found a pretty big difference between the high noise and the low noise. And I kind of wanted to skip over the version of that other plot, which essentially shows low noise looks exactly the same as the earlier one, and high noise is kind of impeded. and look at the dynamics of what people are actually doing in this environment. Okay, so this is a plot showing the proportion of agents that are in these 3 different states under different background values. So if I'm currently at a location in the field where the score is 1, the highest value that that I can get, you see that I'm much more likely to be in an exploiting state. And we kind of automatically coded these states in a model-based way. So overall, as the value that I'm at gets higher, I'm more likely to kind of make an exploit decision as opposed to leaving that location and exploring. So that checks out. And I'm also kind of intriguingly less likely to copy at those high values. So if I'm getting mine, I don't necessarily need to be super drawn toward what other people are doing, even if it looks good. Okay, so what do we see when we contrast these high noise and low noise conditions? Well, we find that participants start exploiting at much lower reward values. So if I find any spot that is getting me, 0.5, say, I might take it, right? If it's in a noisy environment. And what we can see is that actually really interferes with the ability to do social learning, because now the signature of kind of what looks like someone's at a high reward location is now somewhat of a false alarm. So basically, if you see someone exploiting in the high noise condition, it's no longer a great signal as to their actual reward. So we were interested in this as a case, not necessarily where social inference backfires, because people are able to modulate their copying accordingly, but a case where these kinds of strategies, based on making inferences, like if those inferences are harder to make, then you're not going to get as much benefit from them. So this is kind of, I think, a nice illustration of the consequences for groups that individual social inference mechanisms may have. So when rewards are hidden, the ability to make these inferences kind of changes the trajectory of bigger groups in a kind of qualitatively interesting way. Okay, so in the second part of the talk, I want to move on to another setting for collaboration, this time with language and communication. So one kind of feature of this environment was that we took away the ability of players to explicitly communicate with words, so you had to use these kind of behavioral traces. But in kind of the study of, I don't know, signaling systems and language, language is just kind of another kind of external behavior trace that you can make inferences from, right? So like somebody choosing to say something is similarly the basis for a social inference about what's in their head. And I kind of want to show how classical models of communication break down in these situations where you don't really have good words for things, and social inference can kind of help you recover from that. Okay, so here's kind of a very traditional picture of what communication looks like. So this is essentially going all the way back to Saussure, and Shannon, capturing this idea that communication is essentially a transmission problem. I have something in my head as a speaker. I'm trying to encode that into an external message, maybe in language, maybe in a telegraph, beeps and boops, but in some kind of signal that's perceptible to other people. And then they're trying to decode that back into what was in my head, using ideally the same function. So this critically depends on what we call shared conventions. So essentially, this kind of scheme only really works if we have the same dictionaries in our heads that we can use to translate between concepts and external signals. Okay, so this works really well for the kinds of like artificial telecom systems that Shannon was working with, right? Where you actually get to design the terminals and you can ensure that, you know, the telegraph operators at the different, you know, stations are using the same code book. But real world language use is much harder in this regard. Okay, so here's some, you know, I'm going to show you an example. And, you know, coming at this problem from modern computational cognitive science, I think you'll notice a few features that make it a little harder. So I always run into trouble when people try to talk to me about baseball. So I don't know, this is like, you know, how popular baseball is for all of you, but in the United States, it's huge, right? So here's an article written in English. Will the Mets make Kansas City expand? Just as the Mets should consider grooving fewer first inning pitches to Escobar, they might also benefit from pitching around other Royals. Even more so than expected, New York has had trouble getting swings and misses, as exemplified by DeGrom's first ever failure to get a whiff with his fastball. So I don't know what any of these things are, okay? What's a fastball? What's a four-seamer? How do you groove a pitch? What kind of Royals are we talking about here, right? So, you know, this is written in English for an English-speaking community. I'm a L1 English speaker, but that doesn't mean that every communicative act is equally comprehensible to every audience, right? So the first challenge, I think, here that this displays is the challenge of variability in the population. So different people are essentially using different functions to make meaning of communicative signals. So you can't actually use a monolithic set of signals for everybody. And I'd argue that this is, you know, baseball is not the only place that this appears. It's true for all kinds of slang, lingo, acronyms, technical jargon, probably lots of stuff that you've encountered so far at this summer school. So different people know different words. Now here's the second challenge. And again, just to kind of like signpost what I'm doing here, this is like a way that one can think as a computational researcher is like, what are the computational like features of the problem that agents have to solve, right? And one of them is this problem of variability. Another problem that agents have to solve is non-stationarity. Okay, so non-stationarity is essentially a property that means we need to be able to talk about new things. So any static mental dictionary written down at a particular point in time is going to be outdated pretty quickly. So, you know, to take a really extreme example, if you kind of formed your function f that you're going to use to encode and decode messages in the 18th century, it wouldn't have anything about baseball at all because the game hadn't really been invented yet, right? So all of these kind of technical terms and batters and fastballs and bases and strikes and so forth, none of that would be in there. So as long as we're still kind of coming up with new things and expanding our concepts, we need the ability to communicate in cases where we don't already have a ready-made kind of signal for the thing that we want to convey. So this is just like another way of saying, like, when people feel like, oh, I don't have words for that, what do they do? And then the final challenge I want to highlight here is the problem of generalization. And I think that this is probably the most dramatically underappreciated problem in agent-based modeling that I'm going to get into in a second, which is that if you're interested in things like F that are conventions, right, that essentially what makes F work is that everyone else is using the same F. And we know from the existence of many different languages that there are many different Fs that work equally well as long as everyone shares them, right? So these kinds of objects, linguistic conventions, are properties of entire collectives. They're properties of communities. But as agents, we only get to interact with individuals. We don't get direct access to this kind of abstraction of the community. So this is an inductive problem, okay? And an inductive problem means we have to, in some sense, go beyond the data that we have to make guesses about like strangers, right? So I've never met most people in this room, but I'm kind of talking as though you're understanding me, but I don't know that. And I don't really have any concrete reason to suggest that any particular one of you, having not actually interacted with you before, like, how do I know I can use all these words? Well, I'm kind of making a guess based on the fact that I've talked to lots of people in English-speaking communities, and it's worked, for those people. So like, I kind of have to make a guess at some point when I'm interacting with new people. So what do I make that guess based on? Okay, so I want to walk through a couple ways that previous models have kind of tried to meet these desiderata, and show a couple ways that they've fallen short. So there's a class of models that I'm going to refer to as complete pooling models. So some of you may be familiar with these models going back to Luke Steele's and others in the kind of language evolution community, where you essentially put agents on a big network, you have them interact with their neighbors, and they basically do this super simple kind of updating. And here's a little illustration of it. So, I'm, node 33, and I interact with my partner 32, and they use a certain signal to refer to something. Okay, I put that in my memory. So I keep track of the fact that someone said A. Now I interact with another partner and they say B. So I put that in my memory, and I do this with a bunch of different partners. And now I have this big memory bank of the way that a bunch of people have referred to this thing. And when it's my turn to refer to it, I might do something like take a majority vote, right? So that's a really simple agent-based model. And you can show that this allows conventions to emerge in this network. So big networks, even though they're very distributed and don't have any kind of central authority figure, can kind of reach consensus on a shared language. So that's really cool. So like, what's the problem? We call these complete pooling models because essentially the agents in these models don't keep track of who said what. So essentially you're chunking everything into a common pool and updating kind of a single lexicon in your head that you're going to use with everybody, regardless of who they are. So this clearly solves the generalization problem. That's good. It basically, like, if you just treat everybody as the same, you generalize because you're not keeping track of whether someone's new or not. And it solves the non-stationarity problems. So if something new pops up, you'll take a hit in communication for a little bit, but it's you'll eventually be able to converge on something. But what it doesn't solve is the variability problem. So because you're not differentiating between different partners or contexts, you actually have a hard time handling real world kinds of interactions. So kind of these anonymous matching with different partners that you don't even know their identity, may be realistic for certain kinds of conventions like driving, right? So most cars we pass on the road, we never see again, and we don't know who's in them, right? So that checks out. This kind of model works great for that. We want to learn which side of the road to drive on in a way that's going to work with just like any new driver that pops up in the distribution. But in communication, most of our interactions look more like this, where we talk to one person for a while and we know who they are. They're like our best friends, or they might be like Charlie, who, you know, is some of our best friends. They sorry, it might be like your mom or something, right? So you have like this extended interaction with the same partner, and then you might switch to a different partner. And what we know from human experiments in psycholinguistics, this is classic work by Dina Wilkes-Gibbs and Herb Clark, my patron saints, people really care about these partner boundaries. Okay, so if I interact with one person for like a while, and then they leave and someone else comes in the door, I don't assume that all of the things that I coordinated on with the first partner will be true for the second partner. So this is like a little plot showing basically you get much more effective communicating with one partner, but if they leave, you kind of revert back to the kinds of messages that you said at the beginning of your first interaction, rather than the kind of more efficient things that you converged on near the end of that interaction. So you're basically doing some convention formation with a partner, but you're not expecting a random new person to necessarily share all of those things. So this is a property called common ground that Herb Clark has spent a lot of years working on. So you might think, okay, if you're an agent-based modeler, you're like, okay, I could patch this up, right? No problem. I'm gonna put in a partner indexed memory. Okay, so maybe I have one memory bank for 32, and when node 32 pops up, I draw from that memory bank. When 10 pops up, I draw from that memory bank, and I kind of keep them separated. So this is a no pooling model. It's a thing you can do. This solves the variability problem. It solves the non-stationarity problem, but it doesn't solve the generalization problem, right? So like if you encounter a new node that you've never seen before, what do? You don't have a memory bank from them yet, so you have to start from scratch. So you may see where I'm headed with this, which is this hierarchical inference model where you're basically trying to get the best of both worlds. And this is a very natural model to write down in a Bayesian framework. So essentially, you assume that all partners are drawn from a shared distribution, so they have something in common with one another, right? Some parameters give rise to all the distribution of all of your partners. But as you interact with a particular partner more, and you get observations of exactly how that partner communicates, you can kind of dial in a partner-specific model that might deviate from the group mean. Okay, so this is an adaptive coordination model. So on the fly, as you interact with a person, you're kind of forming a individual model of how they work. But yeah, okay, so I'm going to walk you through this. So before I go too far, so there's three basic mechanisms that are instantiated here that I want to draw your attention to. So in this model, one really conceptually important move, although it's somewhat subtle, is that you're introducing uncertainty about meaning. So rather than having like a mental lexicon, which is just like a big list or a big dictionary, you have a probability that such and such a concept corresponds to such and such a word, and it's usually not 0 or 1, it's graded. Okay, so, you know, if I walk into a room with somebody, I may not know ahead of time whether they have access to a certain like technical piece of jargon from, I don't know, machine learning or something, right? Like if I say CNN, I'm pretty sure most people are gonna know the like TV network in America, at least. but like they may not know convolutional neural nets or something. And that has a lower probability, but still non-zero probability. So that this is kind of a gradedness about meaning that we can have priors on, right? So we can have like not 100% confident, not 0% confident, but somewhere in between. We have this ability to do partner-specific learning, so dial in partner-specific parameters that we want to acquire. And importantly, learning about one partner actually does tell you something about the distribution that they come from, right? So it doesn't tell you everything. It doesn't tell you the variance. But if you interact with enough people, you can get a pretty good sense of like what is shared, kind of what can you abstract away from any individual, and what is kind of idiosyncratic about each person. Like your mom has some weird catchphrase that she says all the time, and you don't expect anyone else to say that. Okay, so how do we test this model? Yeah, and I guess I want to say too that this, if you know like mixed effects models for like data analysis, this is just that. So like a hierarchical partial pooling model is basically the same thing that adding random effects to a data analysis model is doing, where you're kind of sharing statistical strength, is kind of the blessing of abstraction and sharing of statistical strength across exemplars. So like you have, 10 participants, even if like you don't have that much data for each individual participant, you can make predictions about an 11th participant. But if you have like a particular participant where you have like 1,000 data points for them, then you basically ignore your prior and you just like have a super well calibrated participant specific model. So this is like hopefully familiar, like just wanted to help make that connection. Although it's Bayesian, which we could talk later about what that means. Okay, so how do we test the predictions of this model? Well, the main thing we're interested in is what happens at these partner boundaries. So as you interact with more people, we predict that something, basically these models come apart at the partner boundaries. So we designed this big web experiment where we connected groups of 4 people in a little environments. This time it wasn't like a fish tank, it was like a chat room kind of setup where they had a bunch of kind of weird shapes that they had to refer to, and had kind of a free chat box that they could use to type whatever they wanted to try to convey that information. So they do a whole repeated interaction with one partner, like in the classic Herb-Clark work, and then they switch partners. So you were previously playing with, say, the blue person, and now you're playing with the purple person. And you know this because you see their avatar. And then after another kind of repeated game with the second person, you switch partners again to the third person. Okay, so what do we predict from our models? Well, the complete pooling model predicts a curve kind of like this in terms of the effectiveness of communication. So as you coordinate with your first partner, you get better, and you basically carry that over in what you're saying to the next partner. So you basically just like treat the second partner as a continuation of the first interaction. Where'd it go? Sorry. We're back. Okay. So you basically treat the second and third partners as continuations of the same interaction. A no pooling model, you would predict something like this, where you get better with each partner, but you basically start over as you kind of have to instantiate a new memory bank for the new partner. And a partial pooling model kind of has a combination of these qualitative features. So you do see this big jump, right, at each partner boundary as you change your expectations about the new partner versus the old partner, but there's some savings. So essentially, like when you encounter your third partner, you're going to carry over some stuff from the first two. So it's this kind of graded pattern. And what we found in our empirical data really only matched the qualitative predictions of that partial pooling model. So we saw these big jumps at boundaries, but we also saw this kind of gradual efficiency changing over the course of multiple partners. So basically, people are not fully returning to baseline like they would under a no pooling model. Okay, you might worry, okay, that is just a measure of what the speaker is willing to say to this new person. So they're basically just getting lazy or something, right? They're just saying more efficient things because they're getting tired. But if we're interested in kind of collective behavior, what we're interested in are these network level phenomena. So does the network converge? Is there actual consensus across the network? And we see a similar differentiation of predictions here. So actually, the easiest one to understand, I think, is the no pooling model. So what these curves are showing is the alignment between what different people in a network are saying at a given time. So if I take a snapshot, there's pair 1 and pair 2. And you want to know the people that are currently interacting, are they using the same signals? That's the solid line. And the dashed line is across pairs. So it's basically, even though I'm not interacting with you right now, are we still using the same language? So that is an indication of whether the kind of network is reaching convergence. And what you see in the no pooling case, as you would expect, is that partners that are interacting are adapting to one another and align really well, but there's never any increase in alignment above baseline for the network as a whole, because I'm starting from scratch with each partner. A complete pooling model, you get that increase in cross-network convergence, like the Steele's models, agent-based models predict. And if you kept this going, eventually everyone would be using the same words. But there's this interference where you actually are kind of a little too rigidly bringing in the stuff from your previous interactions into the new interaction when it's not justified. So you actually, like, previous things are actually interfering with your ability to adapt to your new partner because you're overweighting things that don't actually carry any information. And then the partial pooling model gets this really nice pair of patterns where internally participants are able to perfectly adapt to one another without overweighting previous experiences, but there's an overall convergence of the network over time. And that is what we found in our empirical data. So this is really a collective behavior phenomenon, not just a kind of motivational phenomenon or something. Okay, so wrapping up, I think that these are two cases where understanding agents in a slightly more sophisticated way, so not just as kind of heuristic agents copying or imitating, and not just having like a Steele style keeping a list of things that I've seen before and doing a majority vote or something, but like having a genuine cognitive model of the kind that we've been developing in computational cognitive science for the past 20 years goes a long way in explaining collective behaviors that are difficult to achieve through these kind of simpler agents. Okay, so broadly, the kind of, I think, research program I'm advocating here is spanning levels of analysis, spanning units of social organization, spanning timescales from what's going on in an individual's head And we know that most agent-based models are not good agent models, right? They don't actually explain what individual agents are representing and reasoning about. But at the population level, we also want to capture these like collective phenomena that agent-based models have been extremely good at shedding light on, that our cognitive models have not often been used to make a connection. So I really want to put these pieces together and show that having realistic models of agent cognition actually does have consequences for interacting dyads, for interacting communities, and populations of many different communities. So with that, I'll open it up for questions.
Thank you very much, Robert. So we're doing the Q&A a little bit differently for this session. So come on up, maybe form a line over here, and then you can present your question to the microphone. And I'm also going to change the pin so you can see yourself as well. Okay, cool. So if anyone has any questions, maybe come and line up. So maybe just to kick things off a little bit, Robert, I wanted to ask you about the first project where in that original Beardall fish study, right? They didn't have any social inference, right? They weren't doing any kind of inference process, but they were still able to, I think, get better tracking performance as a function of group size as well. So I guess clearly humans are not doing the same kind of fish schooling behavior as they're doing, but are you able to kind of account for just some sort of general kind of conformist or like type of behaviors in the absence of social inference?
Yeah, that's a great question. So I will say we wanted to avoid making super strong comparisons between fish and people, obviously, because like I think that originally we were like joking about doing like a people are smarter than fish kind of like thing, which is kind of not that helpful. Because a bunch of things are different in these tasks, right? For one thing, people get this kind of top-down view. They have different motor affordances. It's like, you can't just like compare the curves. But there are kind of two things that I think are maybe interesting to highlight. So for one thing, we do find a benefit of the kind of fish. So in the Birdall paper, and I should say Andrew is also an author on this paper. So we were trying to get his expertise on the kind of animal models as well. This move to center heuristic, or this kind of like biasing of the heading direction toward the group centroid, it does get you benefits of bigger groups, right? Like this curve is above baseline. So we're not saying that there's no way of that making groups better. And if you get a much bigger group, it actually eventually does scale, right? So that's kind of the second observation, which is that another way we were kind of thinking of framing this before we stopped making any comparisons between fish and people were like, fish may need much bigger groups to get the same advantages as humans do in much smaller groups. So you can have a human group of like 4 people that already is getting really big advantages of like the whole is greater than the sum of the parts that a fish school might need like 100 fish to get or something. So you could think of it that way too, as kind of like, you know, like the fish sensing can eventually get to the same levels, but it requires a lot more.
Very cool. So we can kind of trade off numbers for quality, right?
Yeah, exactly. Cool.
I just want to quickly change this to near the screen. And then, oops, sorry. Back to the Zoom. Any other questions? Just come line up, and then you can also. Yeah, I just want to the front, and then speak into that microphone that's up there, and you should see.
Hi, thanks for a great talk. So I had some specific questions on this project. So it looks to me like the social inference model kind of, the mean score plateaus off after around 4 people in the group in the model predictions. And then I'm noticing in the empirical data that when the group size is 4, it looks like there's a little bit of a drop off where the performance looks more similar to a group size of 1 than a group size of 3. So I was wondering in the empirical data if it's possible that people are kind of switching strategies once the group size gets to be large enough. And I was thinking that doing social inference is pretty hard and possibly like computationally costly. And once you have a group size that's like 4 or more, maybe you're no longer doing inference over every single person all the time. And maybe you're kind of like trying to allocate your attention in some other way. Like I'm almost relating it to like multiple object tracking or something like that. Anyway, so I was wondering if you could talk more about like capacity limits for social inference models and like what you think is going on here, both in the model simulations and the empirical data, and kind of why the empirical data have that drop off.
That's an extremely insightful question. Yeah, and we should talk more offline because I've been thinking a lot more about these issues. So I guess here again, 2 things. So the first thing is that for the purposes of getting through everything, I kind of omitted some of the details about the model. So there's some parameters to the social inference model. One of them is essentially like a noisiness thing, which is like how likely are you to exploit even when there's nothing there, right? How likely are you to kind of explore even though you inferred someone else had a reward? So there's some moving parts, and actually many of those do much better than people. Okay, so like under many of those circumstances, it just like blows up really fast, because if you basically have no noise at all, and as soon as anyone like does something like stopping or slowing down and you assume there's no noise in the system, it's just like you always have perfect signal about where the reward is as soon as like one person encounters it. So that plateauing off is kind of a artifact of the noise levels that we had to put in to like get a good quantitative fit to the human curve. So essentially like at these noise levels, to like get down to the level of human performance, like noisiness, like motor noise and so forth, you like start getting like misinformation cascades, basically, where like people will start spuriously copying each other and then copying the spurious copiers, and these kind of classic kind of like folly of crowds type things. So that's, I think, what you're starting to see with the plateauing. But I think that we wanted to avoid making, so that's kind of the first observation, is like, what is going on with that model curve? It looks a little weird. I think that the question of like, we know that some kind of noise or capacity limitations, attentional limitations, have to be in this model to do a good quantitative fit. For the purposes of this paper, we were trying to like keep it mostly at this like MAR computational level of like some social inference is needed to like go above qualitatively this ceiling hit by these other models. But I think that there's a huge open question about like, what is the actual model we need of human capacity in a task like this? And I really like your hypothesis of like there being either like a multiple object tracking style, like capacity limitation, where like if I'm attending over here and somebody up here starts doing some behavior that would be indicative of a reward, I just miss it, right? And actually having like a process level model of those attentional processes, I think could go a long way in explaining like the more quantitative patterns of the empirical data. But I think that if you do that, then you'd also want to like run other experiments to like test those more process level predictions. And we just kind of didn't have space in this paper to get into all of that. But I think it's a super important direction.
Hi, Robert. Thanks for the talk. I was curious about, well, task delegation, because this seems really important for collaboration as well. like how a set of agents decides which of them should do certain tasks. So I was like curious about what factors these agents consider, like how these agents infer like the competencies of other agents to do certain tasks, and also how that interacts with representations of the computations of doing those tasks. Yeah, I'm just curious if you've thought about that space.
Yeah, that's great. That's great. Actually, like you're kind of, this is amusing. There's like a thing that I was working on yesterday, actually, for a paper with Charlie, that I think is trying to get more into that question. So there's this question of like how do you reason about roles? So I was thinking about this in the context. So there's this really nice work by like Sarah Wu and colleagues, and also by like Marco and some folks at DeepMind have all kind of worked on this like overcooked scenario, which I think is a pretty good one for thinking about that kind of division of labor. And the argument here that I was trying to put together is like, you need some kind of ad hoc role assignment where you expect that at least like in the context of this kitchen, people are going to stably claim different subtasks of the thing. So like if you're trying to make a salad where you have to like chop the lettuce, chop the tomato, and put it on a plate, that's like a super simple task. But if everybody's just like doing random parts of it over time, like first I chop a lettuce and then I leave it on the plate, and then I go chop a tomato and then I leave that on the plate, you know, and you pretty quickly like run into these, I don't know, like it just dysfunctional things. So the way that this works in a Bayesian model, like the one we have, is that you have a part of your like agent model that you're doing social inference over is like, what is the policy that another agent is following, right? And you can assume that they're also thinking about you and have this kind of recursive theory of mind. And if you also assume compositionality, which is basically you assume that other agents are kind of chunking this task into like fragments in a similar way as you are, then the planning becomes a lot easier because it's over like a smaller latent space of possible chunks. And Judy tomorrow morning, I believe, is going to tell you more about this in a different task, like a block building task, where you're kind of having to like coordinate on what this representation is along with the language, which is like challenging. But I think that this is kind of an entry point for me, at least, into how to answer that question. So basically you would be able to extend that representation of like in the hierarchical Bayes diagram I showed you, some of those parameters. So in the communication model, those parameters were like, what meanings do people have for words? Like what is their communication model? But you can extend that with other stuff. So a huge kind of part of Bayesian modeling is kind of like lifting more things into the joint inference. And I think that like these kinds of roles, specialized roles, are a very natural thing to lift into that joint inference. And then it becomes kind of a question of like, you have a prior over the different matchings between individuals and kind of chunks of the policy. So that's how I would think about that.
Hi, thanks for the talk. So this is quite similar to the earlier question about the multiple object tracking, and it might in fact be just rewording of the same question. But so with your collective search task, I guess you tried up to 6 participants, but if it's more, it sort of reminded me of one framework for understanding numerosity, where with small numbers, I think it's called subitizing, right? You're using a symbolic process to count, map the symbol to each object, but then once it goes beyond a certain threshold, a different process comes online where it's more like magnitude estimation, and it's a combination of these two things that is goes into numerosity estimation. And if there is this like more for a larger number of other participants, if you need to use this kind of ensemble type of representation, it also seems similar to the perceptual stuff with like Alvarez and Frank Tong do stuff with if you have some visual configuration, you have more efficient like summary representation of that, right? But except in this case, it's more like it's not a visual configuration that you're representing with the summary, but yeah, these like I guess these like probably the radius of the quick turn or something, right? And when these coincide, and I guess we all have this experience where if you if you're given a presentation in front of a large group, sometimes you get the vibe of how the group is responding to your joke or right, but it's not like you're looking at each individual person, but you can still feel. So I'm just wondering, do you think there is this kind of a representation of the group, intention, or and if so, like what kind of cognitive process do you think goes into transferring that, the visual stimulus you see here to that social intentionality representation?
Yeah. That's an incredible question. Actually, we should also talk offline because these are all like things that I'm very interested in pursuing. So I think that the connection to like subitizing versus kind of just kind of statistics is definitely like, I think if you were to go down the path of building a more realistic cognitive model of what people are doing attentionally while playing this game, that's like a very natural thing to plug into the model that we have, right? So it's I think a very tractable direction for extending that model if you're interested in that. And I think it would make better quantitative predictions. Like if you wanted to make predictions at the level of like individual actions, as opposed to just like the group size curve, you would absolutely need that. So that's first thing. Second thing, though, I think there's a very, very deep thing that you're catching on to, though, which is the transition from basically like, how do we reason about groups at all, right? So this is something I was talking about a lot with Amit Goldenberg and some other folks in terms of like, the most naive way of reasoning about a group is aggregating reasoning about individuals, right? So it's like, if you have a group of 5 people, I reason about what A wants, B wants, C wants, D wants, and then I like do some preference aggregation or something, right? And it's like, okay, the group like has this average wanting. But if it's a big enough group, and we make these kind of, attribute assignments all the time of like, oh, the like stadium was excited or something, right? And it's true, even though not every individual was excited, like for the football game or whatever. And I think that there's a really interesting question that those numerosity studies help us answer, which is like, at some point we know it flips, right? Like we know that if you just have 2 people, you're reasoning about individuals. And we know that if you have like 1,000 people, you're reasoning about the crowd as kind of like a super agent with its own beliefs and desires, as kind of like this is actually Max Kleiman-Weiner called it like a theory of minds, which I kind of liked as a way of doing that, of like attributing things at the group level. But it's not clear like what the psychophysical function is, right? So like I feel like drawing on that like Alvarez, Frank Tong stuff like would really help us start mapping out that like transition point and trying to understand like what pushes that around and what it's attributed to.
Thank you.
Thank you.